In this video, we'll begin our discussion of what is called a line integral through eventually will be a vector field. So to begin, we're going to start with an example that feels familiar but kind of described in a different way. So consider a wire in two space that can be represented by the vector valued function r of t, where the I component is t and the j component is 0. So we have, that's just a straight line along the positive x-axis. You can think about it in two space as being on our x-plane from here to there, right? Just a wire though, so straight. So the density of the wire can be modeled by a function. So the function, if I want the density of the wire, all I have to do is pick an xy that I want and plug it in. We want to determine the whole mass of the wire. So the mass of the wire, let me describe the function just a little bit more. I graph this function in 3 space. We can see the wire here is from 0 to 5, right? That's the wire that we're talking about. And then if I want a density value, I would plug in like x is 2, y is 0, and I would get that. And it would tell me the density of that wire at that point. Now, if I wanted the whole thing, I would want to take all those densities and add them up. And that would tell me the density of the whole wire. Now, we could think about this function because we can see it here. And we know it lives when y is 0. That's where it lives in that plane. So if we're talking about adding all that up, we can actually just think about that slice. I put some width here, but that is actually there's no dimension. It's just a sheet of paper, slice. Even though a piece of paper has width, but whatever, yeah. So we have density there in each one, and my function is going to be when y is 0, so I'm just going to call f of xy, f of x, and just kind of put a note, y equals 0. And we can actually find the density of this wire just by thinking of this function in that slice by doing an integral from 0 to 5 of, and we're going to replace the x, whatever it may be, in terms of t inside of there, and we're going to do the integral from of dt. That's going to be adding up every single height across there. So every single point here has a density, and running this dt from 0 to 5 of this x of t inside of our function actually adds every single density up. This was a Calc 2 problem. I hope they did this. We all teach different problems, so sometimes these get put aside. But this is the density described in a different way of r of t. This is really nice because our wire in this case is a straight wire, right? With 0 to 5, we got to let the y equal 0, which allowed us to do this one-dimensional integral. Well, what happens if the wire is not straight, right? We have some wire that runs through here, and we're going to keep it on the xy plane, but what if it just runs on some path? Right, so I'm going to derive this formula for us. Derive it. Just kind of think about it. Consider a wire in 2 space, so same thing, but now it's a generic path. It's not a straight wire, a generic wire. The density of the wire can be modeled by the function f of t, same situation. How can we determine the mass of the wire? Well, the density is just going to be the what we call an integral. It's a line integral, and we just put the path down there. Our path is going to be called c. And we are going to add the densities up across the whole wire. Well, across the whole wire would be ds. Right, we could think about it in arc length, and there's a reason we do this because this is going to allow us to derive something from here. All right, let's set this aside for a moment. We've done this before in the class, but I'm going to do it again. S of t from a to t of the magnitude of r prime of t, d, we want a dummy character in there, so no t, but a u. I think I do that almost every time. That is arc length. If I take ds now, that is going to be, well, the integral, the derivative of an integral is just going to spit out the actual value, or we could call s prime of t dt. That's just taking this side and doing our derivative. Well, that's the derivative of an integral, which is just going to spit out the integrand with the upper bound, and then we still have that dt. So I know I can replace this f, I'm going to change f in terms of t. Right? That's just changing x and y into t's. And then I'm going to replace ds with the magnitude of r prime dt. So the density of this wire can be found that. This is our line integral. This allows us to find density in this case. And other things, there are other ways we could think about this. I think about a snow, if we were at our house and we were walking from our path and we had a path to our car, I think of a line integral of like collecting all the snow on the sidewalk, but the sidewalk has no dimension, right? Or one dimension. It just goes straight. It's a piece of paper. It'd be adding all the snow up, giving us an area. The next example, there's a picture and it shows a better description of what we're actually capturing, that it's a sheet of paper that lives on top of the sidewalk. It's the surface of snow, right? Snow builds, accumulates in different ways. So we'd have different mounds and we would collect all the snow on the sidewalk. All right, we can continue with this calculation by changing our t's. All right, and then I'm going to rewrite something just to connect it to something that we've seen before. This r prime magnitude is the same thing as x prime of t squared plus y prime of t squared dt, right? And my question here is, what if f of x t y of t is equal to 1? What do we get? Well, we get arc length. Right? That is if we cover this out, take that out, that is just the definition for arc length of the curve. So this just adds that density to each part. Right? Adding it up, their derivative or integral, remember, adds everything up on a path. So that with the density function will add the density of our wire or the accumulation of snow. This also will help with temperature, which we'll see in the next example. So our answer here is, what if it was 1? Well, that's just the length of the wire. We get arc length of the wire. All right, and I put our definition down here of our line integral. All we have to do if we have a path, right, and we're trying to evaluate that function along the path and accumulate the snow or the density of the wire or temperature, we just put the function in terms of t of our path, right? It's the function in terms of the path, and then take the derivative of our path magnitude, dt, and it'll get us that line integral. These are very helpful, and we're going to put these in a force field, which is going to be pretty helpful for calculations for work.